Till now we have done Green's function for one-dimensional differential equation. Now we will be taking m-dimensional differential equation. So let's take second order m-dimensional differential. Okay, let's think of a two-dimensional differential equation first here. What a two-dimensional differential equation looks like. Second order two differential equation. Okay, if I am having a second order differential equation, what it will involve? So you will be having like this is partial 2y by partial x partial y. So this is the second derivative, is it? Clear? Then I can be having partial 2y by partial, let's say, oh sorry, let me write some f in the function, okay, plus then I get partial y is this. So if you are having a differential equation involving two variables and two independent parameters x and y, so it will be having double derivatives like this thing plus linear order derivatives. Okay. A linear order would be like this: partial f by partial x plus partial f by partial y plus some constant. So is equal to 0. So you can put some constant, let's say a1, a2, a3, a4, a5. Okay? So this differential equation we call a two-dimensional differential equation, a general second order two-dimensional equation. Okay. So you have this kind of, okay, so you are having this differential operator, this Laplacian. If I write it in only in one dimension, it will be what? Second order derivative, is it? If I write it in two dimensions, so you will be having how many variables? So you need to now take the partial derivative y2. Okay, if you write in the three dimensions, it will be having all the three directions like this. Okay, so this is in German. Okay, so this is a second order differential operator. Clear? Okay, so this is a very general second order a two-dimensional second order differential equation. Clear? So because if you, how many variables you get here? Only two variables, x and y, is it? Differentiation is with respect to only x and y. You can put this in matrix form. This very part. Okay, let's put this in the matrix form. It will be like this thing. Anybody? Huh? So do you see there is some off diagonal term? So you are having a cross term. Cross term means off diagonal term. It is a cross term, is it? So you can bring another cross term like this thing. Partial 2f by partial y partial x. Is that true? So let's try something a1 and a1 bar kind of. Okay? So is this, so these two terms, there will be 6 terms. So these now, so this is a cross term, this is a cross term, these are direct term. You can think these two terms on the diagonal. Okay? So let's try this this very operator in this fashion. Okay? So you can write like this: partial 2f by partial xi partial xg. Let's write some aij here. Clear? So aij. Okay, so you can write simply this way: aij. Simple. Forget that. So you can simply write it. Is this a matrix? Do you think this forms a this forms a matrix? Do you think so? So you will be having like this. Okay, let's put the coefficients. Okay, let's put the coefficients. So you will be having, let's say, the coefficient of this thing. So let's call this as A2. Then you are having A3 here. this coefficient can be here a1 because these are cross terms. So this represents partial 2 by partial x2. So this will represent the partial x partial y, and this will represent what? Partial y partial x. So it will be a1 bar. So it will represent partial 2 by partial y partial x, and this will represent what? Partial 2 partial y. Clear? So you can put it in the matrix form plus the linear terms. So the second order terms you can think as a matrix. Clear? Got it? So this is the way you can think it as. Okay, so you can bring this into the diagonal form. Okay, so this can be a diagonalizer. This if the determinant of this matrix is non-zero. Okay, let's say A1 is 0. It means A1 is 0. So these two terms are not there, is it? So you will be having only these two terms in this differential equation. Clear? So that means you are having only the diagonal thing. Eh? Look here. So this is a diagonal operator. Is it? Is this a diagonal operator? Why? Because you are having only what terms? You don't have any cross terms in this Laplacian. So that means if you are having any cross terms, okay, in a given differential equation, you can diagonalize, okay, you can put that into that form, okay, by suitable transformation. Clear? You got it? So this is an idea. Okay, now let's try the m dimensional. M dimensional means you are having now how many variables? M variables. Yes. Any question? Huh? Okay. Okay, so let me write this way. Partial 2 y by partial xi partial xj, okay, where I goes from 1 to m, you can say, and j goes from 1 to m. Let me multiply it by some aij and some over I and j. Clear? So they go from 1 to m. Okay, so these are all which terms? Second order terms. Clear? So then you can put the linear order terms. Okay, so let me use the notation. Okay, linear order terms, let me write something. Okay. Partial y by partial xj, simply linear derivatives with respect. Let's write this bj of x. Okay, this can be in general the function of x. Okay, these coefficients is j goes from 1 to m. Okay, so these are all linear order terms plus some, let's say some c of x and y, that's equal to 0. Is this now second order differential equation? Yes, it's in m dimension. It contains m variables. Clear? So now if you see this is in general, now this very matrix, okay? So this is a matrix. So this is in x, not t. So this very matrix, this is, okay, you can diagonalize it if its determinant is equal to, is non-zero. If the determinant of this matrix is non-zero, you can diagonalize it, is it? So let's write the eigenvalues. Let's call some a's, okay? A's or some a's or eigenvalues of this aij. Okay, so these are the functions of x. Clear? That means if I make some suitable transformation, I can diagonalize it. What I mean by that, so I can write it like this thing. I is running from 1 to m. So you write simply the eigenvalues ai of x. So partial 2y by partial xi, like this thing. Simple derivative, simple second order differentiation. So let me write, these will not change, although they will remain linear derivatives. Okay, so only the coefficients will change. Okay, so b will go to some another variable and c will go to another variable. Okay, but the derivative, this will be linear derivative and you are having a linear term. Clear? So let me write for that as a function f. This function. So what it is function of? It's function of some y and its derivative, partial y by partial x and some constants. Let me put those constants. Okay, let's write simply xy. Okay, x, y, and the derivative. So this contains all these terms. Okay, so once you change, let's say you make a coordinate transformation, you arrive at some new terms. Those will be dependent on x, y, and this derivative. So this, you don't need to do this in a general, but I am just saying so you can have this kind of differential equation in m dimensions. Now look here. So look at this very differential operator. So this is in 3 dimensions, is it? Do you have any linear derivative? Oh, now what are a's? What is a here? So it is 1, 1, and 1, is it? So these are unity. Clear? So this is in the diagonal form. Huh? So that means the eigenvalues. That means eigenvalues of that capital Aij, which are ai. Those are simply identity here. Now what is f in this case? What is f? 0, because it's not there. Huh? You don't have linear order terms here. Okay, now if you are having, think of Legendre equation, or think of the Hermite equation. Huh? So you are having what terms? Second order terms, is it? The diagonal, that is actually one dimensional equation. Okay, d2y by dx2 plus some first order term. Okay, so you are having like this thing, d2y by dx2 with certain coefficients, let's say c, dy by dx plus some another coefficient of y is equal to 0, is it? So all those equations are of this form. Huh? Let's say b here. You are having 1 minus x square here and some here and some here, is it? You remember it? Okay, so these are the general equations you have studied. Now is this in a diagonal form? Yes. Is it? Because it's only in the one dimension. What is a here? This a. It's b. Is it? Now what are the f? F is actually this very term, dy by dx and y. Got it? So Samashaman? Because okay, this is also dependent on x, because the c and d are actually functions of x. Samashaman, the equations you have studied, Legendre equation, Hermite equation, and all those equations. You have done those in your mathematical physics course? Huh? Okay, good. Now we can classify equations based on this A. Okay. So let me write. So we are having 3 types of equations. Okay, 3 types of differential equations we can have. First is what we call the elliptic equation. Elliptic type. Okay? Okay, if all coefficients a I of x, okay, at some point x, at x naught, so you are evaluating these coefficients at some point x naught, okay, okay, are non-zero and have same sign. So all these coefficients are having same sign, that means whether they are positive, all will be positive, they are negative, all will be negative, is it? Okay, so and they are non-zero at that point. So what type of equation we call that? It's an elliptic type second order differential equation. Now look at this thing. Okay, so what are the coefficients here? It's 1, 1, 1. All are non-zero, is it? And all are having same sign. Okay. So now let's take another this thing. So we call that as, let's say, ultra hyperbolic. Okay. So if all aix at some point x naught are non-zero, so this must be non-zero and have different signs. Okay, it's not necessary. So, or they can be having coefficients can be having different signs, is it? So we call them as ultra hyperbolic. But if only one of the coefficients, okay, have a sign different from the rest, then the equation is said to be hyperbolic. Clear? So we are having elliptic type and hyperbolic. Can anybody give me an example of hyperbolic type differential equation? So let's take second order differential equation. So let's take this DLM version. Okay. This how we write it? Partial 2 by partial t to c square. Okay, minus then lambda square. Is it? Is it true? So either you can put minus here or plus here. So if I put minus here, let's put it here plus. So what you are having here? So you are having at least one is having minus sign. So this is a hyperbolic differential equation. I mean differential operator. Okay, so you can have another type, what we call the parabolic type. If at least one of the coefficients ai x and x0 is 0. So that means one of the coefficients is equal to 0. Clear? So it's called a parabolic. So sign does not matter. One of the coefficients should be 0. So this is the general type of second order m-dimensional differential equation what you can have. Okay, whether you can be having one dimensional or two dimensional, three dimensional, and so on. Broadly, you can classify these differential equations into three types. Okay. So now let's move ahead. Right? Let's start to figure out the Green's function. Okay. Everybody has written it? Huh? So now let's convert the delta function, okay, to a given coordinate system. So we can write down this Lx. So while Lx is the m-dimensional second order differential operator, okay, acting on the g of xy. So let's write now. Okay. So these are the coordinates, sir. These are no vectors, sir. These are not single variables. This means differentiation with respect to all x coordinates. Clear? So I can write this. So this is an m-dimensional delta function. We have this x actually. You can write it as x1, x2. These are all the coordinates. Okay, and y is equal to y1. Okay, so this is an m-dimensional vector, you can say. Okay. So we write this delta of x minus y as delta of x1 minus y1, x2 minus y2 dash delta of xm minus ym. Okay, so this we can write in the product form. I is running from 1 to m, delta xi minus 1. Clear? So this is your m-Dirac-Delta function in Cartesian coordinate system. Okay, so now let's make a transformation from one coordinate system to the another coordinate system. Clear? So let's think you are at a point P, some arbitrary point, and then you try to transform, let's say, from Cartesian coordinate system to the spherical polar coordinate system, is it? So you know how the coordinates are related. Clear? So let me try to do it in a more general way. Okay. So we are making a coordinate transformation, right? Okay. Let's make a coordinate transformation. Okay. From x1 to xm to some new coordinate system, zeta defined as zeta1 to zeta m. Okay. By, so there will be a transformation function which will transform from zetas to x or x to zeta. Let's call that function as f. So what I mean by that, so I'm like this in x1 is equal to f1, so zeta1 is zeta m. So this is how, okay, all these coordinates. So I am assuming, so my transformation is invertible at all points. Okay. So I am not assuming here there is any kind of singularity here. So we are assuming the transformations are what? Invertible. What I mean by that, so you can go from zetas to x or x's to zeta. Okay. So that is, this function is actually invertible function. Okay. So or I can write like this in general. Xi is equal to fi zeta1 zeta m. That's actually equal to fi zeta I is 1. Clear? So it's simple. These are the trivial things what I am doing. Okay. So let's take a point P. Okay. Let's assume a point P. It is simply the observation point. Think of a point on a sphere, on the surface of a sphere, is it? So you take an arbitrary point on the surface of the sphere. So you can specify the coordinates in spherical polar coordinates r, theta and phi, or you can specify its coordinates in Cartesian coordinates, is it? X, y and z. Clear? So let me specify for that very point what are the coordinates. Let's assume certain coordinates in zeta coordinate system and in Cartesian coordinate system for that very point. Okay? So let's assume a point P having coordinates. Okay? So let me write A1 dash dash AM. So its coordinates are these. Okay, when you specify a point, you need to specify r, theta and phi, let's say, on the surface of the sphere, is it? Or you need to specify x, y and z. Let's specify in, let's say, in Cartesian coordinate system, for this very point, you are having the coordinates, these, you have specified the point. Okay, so let's say x1 is equal to a1, x2 is equal to a2, and so on, xm is equal to am. Okay, in Cartesian coordinate system. Okay, and I am having, let's say, let me write alpha 1 dash dash alpha m in that zeta coordinate system. Okay, so let's say you are on a certain arbitrary surface. Okay, this is at a point P. You can specify. Okay, so its points are a1, a2 dash dash am. Okay, or its points are what? Alpha 1 dash dash alpha. Clear? So much on? Everybody followed it? Now tell me, what is the relation between this A's and alpha? Anybody? So I have specified, okay, my coordinate system, I have specified the coordinate transformation like this way, okay? And I know for the point P, my coordinates are A's and alphas in two different coordinate systems. Now what is the relation between A and alpha? What is A1 equal to? Huh? A1 is simply you substitute for x1 is equal to A1 and zeta 1 equal to what? Alpha 1 and alpha, is it? So A1 will be simply F1, F1 A1 dash dash A alpha M, is it? So it is like this thing. Okay. So it means A1 rather AI I can simply write Fi alpha 1 dash dash alpha I is done. Clear? समझ हो? Now let's move to the delta function. So this is we specified now the points. Okay. Now we need to do the delta function business. Ultimately, when you move from one coordinate system to another coordinate system, look, differential form of the differential equation will be same. It will be, let's say, if we are taking the second order differential equation, its form will be same, is it? Only the coefficients will get changed, is it? समझ आओ? But what will be changing when I move from one coordinate system to another coordinate system? Delta function. I need to figure out how delta. It will be a delta function, but I need to check how it changes, is it? What is the form of a new delta function? Clear? Okay. So let's take this delta function. So we have, let's assume a function f of x. Okay. Let's write some function f of x. Okay. Multiply it by some this delta function x minus a. Okay. Clear? So and integrate over this x. So what it will be equal to? F of vector a. So is it true? So what is that equal to? So it's simply equal to f of a1 dash dash a. Okay. So what this object is equal to? So or I can write this as okay dx1 dash dash dxm f of x1 dash dash xm. Okay. So what are these delta functions? So it is simply delta x1 minus a1, delta of x2 minus a2 dash dash, delta of xm minus am. Okay. So that's equal to this object f of a1 dash dash a. Okay. So or I can write this way and simply dmx. So this is just for you people to make you understand what I am doing. So x1 dash dash xm. So I can write I is running from 1 to let's say m, delta xi minus ai. Okay. So that's good. So it's simply I am simply rewriting what? Just in what I am doing? I am simply rewriting the same equation. Okay. In the expanded version. Got it? You got it? Okay. So now let's make a transformation. When I make a transformation from one point to the another point, so what I need to define the Jacobian of the transformation, is it? When I let's move to the another transformation, then what I need to do? Okay. So if I go from so you go from let's say x to zeta, so then I need to define Jacobian. So let's say Jacobian of the transformation is it is the determinant of what? Partial xi by partial zeta j of this very matrix. Clear? So while I and j are running from 1 to, so this is the matrix. So now what it implies? So it implies this dmx will go as j bm zeta. True? Tisha? Integration measure will change. It will get simply multiplied by the Jacobian. समझ आओ? So now let's apply it here. Now let's write. Okay. So write it. So therefore, I can write these equations. Let's call this equation as first equation 1. Okay. So dm of x I can write dm of zeta and a Jacobian. Clear? Now tell me, what about f? What will happen to f? x1 will change, is it? Because when we are moving from one coordinate system to the another coordinate system, coordinates will get changed. How I will write x1? There is a relation between x and zeta, is it? How is that defined? x1 is defined as f1 zeta 1. Okay, great. So I will write it as simply f1 of zeta. Okay? Zeta vector. I will not put zeta 1, zeta 2 and so on. So it is the function of zeta. What about x2? f2 on zeta. Okay? Dash 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 fm of zeta. What about these delta functions? Okay, now what is xi? Xi is simply fi zeta. Okay, minus what is ai? It's again fi but alpha. Because ai's are related to alpha, is it? So what is that equal to? So it's equal to tell me f of what is a1? So it will be simply f1 of alpha, f2 of alpha, dash dash f. Clear? समझ आओ? Is it? Any problem? Now if you see if you look at this very differential equation, sorry, if you look at this very integral equation, okay, so okay, forget about the j for the moment. Okay, so let's look at this delta function. Is it? Forget about the j. So it means you are having the same kind of fx multiplying the delta of x minus a. Is it? So it means all these f1s are replaced by what? F alphas. So Mushama, is that true? So it means the j times this object forms a delta function. So in other words, your delta function is scalar by what factor? J. We know this, okay. We know this identity. So you are having this identity, let's say dx, f of x and delta of x minus a. So how you write it as? F of a. Is it true? So this is the general definition. So now if I look at this thing, so it means if I multiply this j, so this object is scalar by j. So this multiplied by this gives me this kind of result. Okay? In other words, your delta function in new coordinate system is what? J times this object. Got it? समझ आओ? Huh? So let me extend it a bit. So which will be useful in a moment. So I can write this thing dx1, sorry, d zeta 1 dash dash d zeta m. Okay, so I will write like this thing f of f1 zeta, okay, dash dash fm zeta. Okay, so this is equal to, I will write j times this delta of f1 of zeta minus f1 of alpha, like this thing. So multiplied by, so these are how many delta functions? M delta functions, like this thing. Okay, delta of fm of zeta minus fm of alpha. Okay, so that's equal to f of f1 alpha dash 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 fm. Okay, so don't put square bracket. Square bracket has a different meaning in case of functions. So let's call this equation as 2. Okay. समझ आओ? So in other words, can I say, okay, now as an observation I can write this. So we observe that this j times delta of f1 of zeta minus f1 of alpha okay, dash dash delta of f m of zeta minus f m of alpha. So this acts in the same way like, anybody? Can anybody tell me in which way it looks like? It looks like this way: zeta 1 minus alpha 1 dash 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 zeta m minus alpha. Okay, so this is multiplication. Do you think so? So it's the behavior of this very delta function is same as what delta function. This, okay, now let's substitute this delta function here. Look, so once I substitute this delta function here, so you are having delta of zeta 1 minus alpha 1. Okay, now look here. So you are having f1 zeta. So that means zeta 1 will be replaced by what? Alpha 1. If you look at this very f1 alpha, what actually it is? f1 alpha 1 dash 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 alpha m. So what about this thing? So it is fm alpha 1 dash 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 alpha m. So what about this f1 zeta? So it's f1 zeta 1 dash 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 zeta m. So if I multiply them by these delta functions, so it means all zetas will be replaced by alpha. So that means this zeta will be replaced by alpha and this zeta will be replaced. So that's why you are having here what? Alpha. So in other words, this very object, this is a transformer. Okay, in the transformer frame, your delta function is now this thing. So or everybody got it? Or okay. So in other words, I can write it, which implies, okay, j times. So I'll write it simply. I is running from 1 to m delta fi zeta minus fi alpha. Okay, so that's simply equal to summation I is running from 1 to m delta zeta I minus alpha. Okay, clear? Just I put it in the product form. Now this I can write simply j delta m dimensional function. Okay, before doing that, so I can write this as, or I is running from 1 to m. What is fi zeta? Can anyone tell me? It's xi. Is it? Fi zeta is xi simply. So this is simply xi. Okay. So this object is xi, and minus what is fi alpha? It's actually ai. Using the transformation, is it? So this is as such. I is running from 1 to m delta zeta I minus alpha. So now this is actually the delta function in the Cartesian coordinate system, and this is the delta function where? In the transformed frame. So or I can write j times delta of this x minus a, that is same as delta zeta minus alpha. Clear? So or in other words, the delta function that is defined in the Cartesian coordinate system, it transforms as 1 divided by Jacobian. This we have already done earlier, is it? When we are doing the potential due to a line charge. You remember? Huh? When we are applying the cylindrical coordinates. Okay. Okay. So this is, okay, what we have assumed. What was our assumption in deriving this thing? What was our assumption? That there is no singular point in the coordinate system, is it? Clear? So we assumed our coordinates transform from one point to the another, okay, from one system to the another system, is it? Without having a, so it's an invertible transformation at all points, okay? So, decide, right? Okay, so let's assume, okay. So if j is equal to 0 at some point p, what does it mean? So the transformation is single. So you come across actually a singularity in the coordinate transformation. Okay. So it's a coordinate singularity. It's not a singularity in the usual sense what you have done in the complex analysis. So it's simply the coordinate. So that means there are certain points where the Jacobian becomes 0. So let me give you an example. So you are having a Jacobian for this very coordinate system. Cos of theta y is equal to, so cylindrical coordinate system, is it? So you are on the, this is what cross section of the cylinder, that circle, is it? Circular polar coordinates, what you know. Huh? What is the Jacobian if you move from xy to r theta? So the Jacobian here is simply determinant of partial x by partial r, partial y by partial r, and partial x by partial theta, and partial y by partial theta. So you just calculate it, so it will be simply equal to r, is it? So the Jacobian is simply proportional to r here. Huh? Okay. Proper not equal to r. Okay. So where the Jacobian can become 0? So now look here, Jacobian is independent of theta, is it? So it only depends on r. Now why this Jacobian can become 0? R is equal to 0. So that means you are having x equal to 0, y is equal to 0 point. That is the origin of the coordinate. Okay. So at r is equal to 0, theta is indeterminate. Okay. So for any value of theta, if you are simply at r equal to 0, so Jacobian is 0. So you cannot determine theta. Eh? Got my point? So that means there arises a coordinate singularity in this very system simply at r equal to 0 for any value of theta. Okay? Got my point? Now if you are having certain variables which you are not able to determine at the point where Jacobian becomes 0. So we call those as ignorable coordinates. So in this case, which is ignorable? Theta. R you have determined r is equal to 0, let's say, and so what is the point? So it's actually 0 theta point, or in other words you are having x equal to 0, y is equal to 0. So in your polar coordinates theta becomes ignorable. Okay, you are not able to determine at the coordinate singularity this very variable. So now if you are having the Jacobian in this is the Jacobian defined over all coordinates. So you have look here, you are taking all coordinates into account, is it? But at certain point it becomes 0. So what to do? Okay, now if I am having r equal to 0, this Jacobian becomes 0. So you are so this is an undefined equation. Clear? So in such case, what to do? Okay, how to proceed that? Eh? So have you got the idea of what ignorable means? So think of a sphere. Okay. So in spherical polar coordinates, again, if you are having r equal to 0, in spherical polar coordinate, what is Jacobian? Spherical polar coordinate. Jacobian is equal to r square sine of theta. Okay, at r equal to 0, what happens to Jacobian? It becomes 0, is it? So whatsoever is the value of theta, so it becomes 0. Clear? So it means theta and phi are ignorable at r equal to 0 at the origin. In spherical polar coordinates, both theta and phi are ignorable. Now let's fix r here. Eh? So you can take what should be the value of theta? It is 0. If I take theta equal to 0 here, you are again having what? An ignorable coordinate. So that means if you are fixing your phi values and r values, that means along the z axis, that will become ignorable. So sorry, there will be coordinate singularity along z axis because theta is defined with respect to what? Z. So you are having z axis and you define an angle of a vector with respect to z. Okay. So now if theta becomes 0, that means the vector is aligned where? Z axis. So that means all the points whatsoever the values of r will be, or values of phi will be. So you are having coordinate singularity along that very axis. Clear? Okay. So now what to do in that case? How we will define this? So this happened actually, this problem arises where? When we defined actually the potential on a line, is it? On a line charge, when I converted from simply Cartesian coordinate system to where? Circular coordinate system, rather the cylindrical coordinate, is it? You remember it? Okay, so there was actually the coordinate singularity. So we removed it by some figure, some technique. So actual truth is here. Oh my god. Okay. So what what is this thing? So it is integral to d zeta omega d zeta m f1 zeta. Okay, so what to do? Let's say you are having, let's take from coordinates k plus 1. Okay. So I should say, let's say zeta of k plus 1, k plus 2, dash 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 up to m are ignorable. Ignorable coordinates. Clear? Samajh? So then what will happen? So I can define now the Jacobian in this way. Okay. Now look here. So I will write this simply as d zeta 1 up to d zeta k. Okay. So the integration in this way. So I'll integrate out the ignorable coordinates. I'll simply integrate over what? Ignorable coordinates. Okay. So I'll write it this way. Jk. Then you are having this f of f1 of zeta. Okay. I will tell you what it means. Fm of zeta. Okay. So multiplied by this delta function. Okay. So let me write simply now it as summation over I is running from 1 to m. Okay. So what it should be? Sorry. K. So delta f of zeta minus f. Okay, let me write first it. So then I'll explain what I have done. So that's simply equal to f of f. Okay. F1 of alpha dash dash f k of alpha. Okay, now compare the two equations. What I have done. So I have defined my Jacobian. The new Jacobian is actually equal to integral. You integrate over the rest of the variables. Okay, you take this Jacobian d zeta k plus 1, d zeta k plus 2 dash dash dash. So you are integrating over actually ignorable coordinates. Clear? So now you have introduced a new Jacobian, which is actually the old Jacobian. Okay, now you substitute it back. What you will get? You will get the same result, is it? So now tell me, does there exist any coordinate singularity in this very delta function? Because jk is defined up to which point? So you are having these are ignorable, and you are having, let's say, zeta 1 up to zeta k. They are not ignorable, is it? So that means when you are taking those coordinates which are not ignorable, you will not arrive at what? At the singularity, is it? So you are removed simply just by integrating out your Jacobian over all these ignorable coordinates. So samajh aawa? You got my point? Got it? So then, okay, so this delta will be simply equal to, okay, now let me rub it. So it means, so the transformation will be simply like this. Okay? Because jk times this is equal to that delta function, is it? So it will be simply jk by. So this is your, now, the transformation rule. Now let's take the example. Okay? So let's take the example. The same thing, eh? So you are having coordinate transformation r cosine of theta, y is equal to r sine of theta. Clear? So much of what is our zeta 1 here? Zeta 1, let's take zeta 1 as r and zeta 2 as theta. So much of? Okay, so let's do it in this way. What is the Jacobian here? It is simply r. Clear? Now tell me how many ignorable coordinates are there? How many total coordinates are here? How many total number of coordinates are only 2, is it? So you are having, okay, this z, okay, so this m is equal to 2, is it? So how many ignorable? 1, is it? So that means you are having ignorable coordinates is equal to 2 minus I need to figure out k, sorry, this k I need to figure out. So non-ignorable coordinates is only one, is it? So you are having one ignorable coordinate and two total coordinates. So non-ignorable coordinate is how many? 1. So that means J1 because I need to calculate J, is it? So then which is J. So therefore I will calculate this J1. K is simply equal to 1. So this is equal to K. So it is integration over Jacobian and then one ignorable coordinate. What is that ignorable coordinate? Theta. So what is the range of theta? 0 to 2 pi. Okay? Because it's on circle. Huh? So on circle it is 0 to 2 pi. So this is simply J is equal to R. So it is 0 to 2 pi R d theta. What is that equal to? 2 pi R. Samajh aa? So that means if I move from circular coordinate system, let's say x minus y, that's equal to delta of x, delta of y if you remember it. So it is simply delta of R. Okay? So samajh aa? It's simply what? Delta of R. Oh, sorry. I should write this. I should have put this. I will assume y equal to 0. So I will take simply this delta of x. So delta of x. So that simply means in the two dimensions it is x and y. I have taken the other point 0. That's okay. I have not shifted the delta function. So that is simply equal to how many ignorable coordinates are there? So these are actually non-ignorable coordinates in this delta function. Okay, look here. So these are all which coordinates? Non-ignorable. This I goes from 1 to k. Rest we are actually integrating out. Samajha? Integration over those very coordinates gives you 1. Samajha? So you are taking only these terms. So it will be simply delta of R divided by the J1. J1 is 2 pi R. This was actually the figure we have derived earlier. Samajha? Clear? So now if I take in the spherical polar coordinates, okay? Let's take, what are the spherical polar coordinates? R sine of theta, sine of phi, y is equal to R sine of theta, cos of phi, and z is equal to R cosine of theta. Is it? Is it? Okay. So you just check whether you are hence okay, just it is. It's okay, huh? So what are okay, what my point is, what is the Jacobian of this transformation? It's simply R sine of theta. When you move from Cartesian to the spherical polar coordinates, the Jacobian turns out to be this thing. Now I need to calculate K. Okay? I need to calculate K. How many non-ignorable coordinates are there in your system, is it? So now if you see this at R equal to 0, this becomes 0, is it? So that means both theta and phi are undetermined. So you are having two ignorable coordinates in this system. So how many number of coordinates are there total? 3 minus 2, so that's equal to 1. So you are having one non-ignorable coordinate. So therefore I can write J1 is equal to then you integrate over the other two coordinates, is it? So Jacobian, okay, the other ignorable coordinates are d theta and d phi. So what is that equal to? So it is simply, okay, Jacobian is r square will come out. So you are having now 0. Okay, let me write it here. So let me write. Okay. So it's equal to r square sine of theta d phi. Okay? Because integration is only over theta and phi, you take r square out. Theta goes from 0 to pi. Okay, then you are having the sine theta d theta, and phi goes from 0 to 2 pi. So it's equal to d phi. How much is that? 4 pi r square. Okay? So if you go from the Cartesian coordinate system, the delta function, delta x, delta y, and delta z. Okay, so that's equal to simply, okay, non-ignorable coordinate, delta of r divided by j1, that's 4 pi r square. समझ आया? You got it? So now let's spherical polar coordinates in m dimensions. Okay, I just look here. Spherical polar coordinate. When you go into the polar coordinates in 3 dimensions, let's say, or in 2 dimensions, what you are having? R cos theta, R sin theta. Is it all these factors were multiplied by R? Is it radius of the sphere or radius of the circle? In 3 dimensions, you are again having R. Is it? Now let's go to the 4 dimensions. You will be having R multiplying. Is it? So how many angles will be there in 4 dimensions? 3 angles. In 2 dimensions, you are having only 1 angle. In 3 dimensions, you are having 2 angles, theta and phi. Now let's go to the 4 dimensions. How many angles you will be having? 3 angles. If you go to the m dimensions, how many angles? M minus 1 angles and 1 radial coordinate R. Is it? So that means if you take the m dimensional spherical polar coordinates, let's say, so all these angles will be ignorable, because at R equal to 0 you cannot determine all these angles. So it means how many non-ignorable coordinate will be there? 1. Okay, m minus 1. So you will be having only how many? Only 1 non-ignorable, that is R, is it? So it means if I am going from, let's say, delta of x, so it's actually the m dimensional x. Okay, let me write it as x1, x2, dash 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 xm. So what you will get? So you will be getting a delta of R divided by what is here? J1. Tisha? What is J1? Can you tell me? J1 is actually equal to integration over J over, let's say, all angles d theta 1, d theta 2 up to d theta m minus 1. Samajh aa? Got it? Huh? You got my point? Okay, so now let's develop what is the Jacobian of the transformation in m dimensions. Okay, let's make by the induction. Huh? Okay, so in 2 dimensions, so what is the Jacobian? R. What is in 3 dimensions? J is equal to R square sin theta. What is in 4 dimensions? Now let's take 4 dimensions. J should be equal to, tell me. Okay, now look here. Can I put it as sine of 0? Can I put raised power 0? It is equal to 1, is it? So then you have increased the power by 1. You have actually multiplied by 1 sine, is it? So what it will be? It will be proportional to R cube. Now you raise 1 power sine square and multiply sine square theta 1 sine of theta 2. Okay? So now you go ahead. So let's take in m dimensions. M dimensions, it will be simply R raised power m minus 1. So now what it will be here? Sine of, yes? M minus 2, good. Then theta 1 and so on up to sine of theta m minus 1. Clear? All other powers, huh? Is it true? Do you agree with it? Okay. So sorry, it should be m minus 2. It should be m minus 2. The power should be here, m minus 2. Okay? So you are look here, you are having 2 here and 2 here. Huh? Got it? So clear? Huh? So now you agree with this very formula? Huh? So this is actually the Jacobian m dimension. Now what I need to calculate? J1, is it? Or summation? So let's calculate J1. Okay. So J1 is equal to, so it will be simply integration over that J, is it? Since you are integrating over theta, I can take R raised for m minus 1 out. Right? So it is m minus 1. So it is integration over this sine of m minus 2 theta 1 dash 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 sine of theta m minus 2 d theta 1 dash 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 d theta m minus 1. Okay. So look here. So you are having theta is up to m minus 2. You are having integration over m minus 1. Look, in case of spherical polar coordinates, you are having integration over d theta that comes with sine theta, and d phi that does not come with any angle, is it? So you are having additional d phi here. The same case arises. So what it will define me? So in 3 dimension, okay, you are having the sine theta d phi. What does integral gives me? It gives me simply solid angle, is it? Solid angle for 3 dimensions, okay? So this is solid angle in 3D. So this is actually the solid angle in m dimensions. Okay? So let's write that as omega m. So omega m is this very integral. Forget about what. I will simply write the value of omega m. So this is solid angle. So that means the J1 is simply equal to r raised power m minus 1 omega m. Where m is the solid angle in, omega m is the solid angle in m dimensions. Clear? So try it. Omega m is actually equal to, okay? So you don't need to actually integrate it directly here. Okay? So can you try it? Can you give it a try? You can prove it by induction as well, or you can do it directly. Okay? So let's try. So it's gamma of m by 2. Gamma function you know, studied it. Okay, divided by mega upon RPC dividends. So 2 pi raised power m. This you have already actually did. 2 into pi raised power m. So this is actually the solid angle in. No. I have written wrong. It's a reverse one. It's 2 pi raised power m divided by gamma. So this is the solid angle. I think this formula you have derived in StatMech. Partition function of a free gas, free particles. You are not done. Partition functions you are not done. You are not calculate partition function. Have you calculated partition function? Huh? What you are doing then? So you are at the end of the course. So you are not done partition function. Yes, tell me. Yes. Have you done partition function for any? Have you studied ensembles?
Yes, sir.
Ensemble is based on the partition function. How you calculate different variables, thermodynamic variables from StatMech? Using the partition function, is it? Have you calculated partition function for, let's say, classical gas in a box?
Yes, sir.
Have you calculated this formula somewhere? Okay, so forget. So therefore I can write this thing as this delta function. Delta of r divided by what is J1? It's r raised power m minus 1 omega m. Okay? So what is that equal to? So it is delta of r. Okay, let me write it simply. Gamma of m by 2 divided by 2 pi raised power m. Okay, delta of r divided by r raised power m minus 1. So this is our delta function in spherical polar coordinates for m dimensions. Clear? So now let's take an example. Let's utilize it. So that will be the end of the formal introduction to Green's function. Then we'll take the problems in the next week. Okay? So let's take this Laplacian operator. Okay? So let's write this Laplacian in m dimensions. Okay? So how I will write this Laplacian in m dimensional? Partial 2 by partial x1 2, partial 2 by partial x2 2, dash dash plus partial 2 by partial x. So this is the Laplacian in m dimensions. And let's try to figure out what is the Green's function corresponding to this Laplacian in m dimensions. Okay? What I need to solve? So I'll write this del Laplace square, okay, acting on this Green's function g of x y. So it is in the m dimensions, okay. So I'll write delta x minus 1. Okay, got it? So if I go to spherical polar coordinates, I can write Laplacian in spherical polar coordinates now. Is it? Is that true? So I can write this in spherical polar coordinates. Okay. Okay, let me put this y equal to 0. Let's put y equal to 0 for simplicity. So that means we are taking our origin. Okay, we are defining a delta function at the origin instead of the offset point at another point. Okay, so it is actually equal to Laplace g of x is equal to. It becomes simple actually to put origin. So now in spherical polar coordinates, this equation can be written as. So what will be the spherical polar coordinates? I'll simply write Laplacian. Okay. Now let me not put x directly there. So let me write the g of x. So it means this object has been put in spherical polar coordinates. I'm not writing explicitly what are the spherical polar coordinates in m dimensions. Okay, how this Laplacian looks like. But I want to tell you something more. Okay, what about this delta function? It will change, is it? In spherical polar coordinates, how it looks like? Tell me. It simply looks as delta of r divided by r raised for m minus 1. Let me write omega m. Omega m means solid angle in m dimension. I will not write now explicitly the value. At the end, we will put the value. Okay? So now look here. So the right hand side only depends on r, is it? Is that true? Okay, so what it means? What it means? So when you are, okay, let's say if you are in simple three-dimensional spherical polar coordinates, so you are having a function depending on only r. That means it does not depend on theta and phi. It's spherically symmetric, is it? So look here, this delta function is spherically symmetric. It does not depend on theta and phi. Clear? It does not depend on angles anymore. It means this g should be spherically symmetric. Clear? So in other words, this g must be dependent on r only. It should not depend on theta and phi or any other angles. Clear? You got it? So guess Karan? You have come to my class for the first time? I have not seen you for many days. Yes, you are. आप कल आए थे? इस वीक में कभी आए थे? कब? हाँ? एग्जाम के दिन? एग्जाम के दिन आए थे? मतलब आज थर्सडे है ना? It's your fourth day. Last week में? अभी attendance check करते हैं. Okay. You got my point? So just from the observation, this g should not depend on what? It should not depend on angles. It is spherically symmetric object. Clear? Okay. So now let's try to evaluate this very thing. So let's take our r. Let's take the radius in m dimensions. Okay? How it should look like? So usually we put x square plus y square plus z square root. Is it? So this r I can write as x1 square plus x2 square plus dash plus xm square. Clear? So this is the radius vector in m dimensions, or the magnitude of the radius in m dimensions. Okay. So now let me define some function f. Let's take partial f by partial r. Okay? Let's make the differentiation. Or let me write like this. Partial f by partial xi I should write. Differentiation with respect to simple coordinate. This x. Okay? So what it will be? So let's use the chain rule. It will be partial f by partial r by partial xi. Okay, so I want to calculate this partial f by partial r, is it? So much sure? But I can, okay, since f depends on all these coordinates, I will calculate this thing from this very object. I will be able to calculate this partial f by partial r. Okay, so what is this partial r by partial xi? Can anyone tell me? You just differentiate it. What it will be? Anybody? It's partial f by partial r. Can anybody tell me? It will be simply xi by r. It is simple differentiation. Okay. What is partial r by partial? Okay, it will be 1 by root of r, is it? Sorry, 1 by root of this thing, that is r. And then you differentiate xi, any xi. So it will be 2xi, is it? 2 and 2 will cancel, it will be xi in there. Okay. So now let's take another derivative, partial by partial xi, like this thing, xi2. So what it will be? So it is partial by partial xi of this partial f by partial r, xi by r. Okay? Whose class is next? Huh? Okay, so this I can write, this partial 2f by partial xi2, that's equal to partial by partial r of this objective, partial f by partial r, xi by r. Okay, then you multiply by partial r by partial xi. Okay, so now let's multiply, let's operate it. It will be partial 2f by partial r2 and xi by r, then minus partial f by partial r, xi by r square. Clear? Because it is a differentiation with respect to r. Okay, so then your what is partial r by partial x? So it's xi by r. Okay, so now you are having xi square, partial 2f by partial r2, xi square by r square minus partial f by partial r, so it's xi square by r cube. It's a simple differentiation I am doing, product rule. So therefore I can write summation over I is running from 1 to m, partial 2f by partial xi2. Okay, so this will actually say, if I sum over I, okay, it will be the Laplacian, is it? Is it true? Is it true? Is this the Laplacian? Laplacian acting on f? So it is partial 2 by partial x1 plus partial 2 by partial x2, so on partial 2 by partial xn. Okay? So it will be simply equal to summation over I is running from 1 to m, partial 2f by partial r2, xi square by r square, minus partial f by partial r, xi square by r. Okay? Okay, so now you sum over I. When you sum over I, it will be x1 square plus x2 square, so on. It will be simply r square, is it? So r square is simply what? Summation over I, xi square. So similarly here, so you are having simply it as partial 2f by partial r2. A term missing. There is one term is missing. Can you tell me? Yes. This xi depends on r, is it? We have not made a differentiation with respect to this xi plus partial f by partial r. So you are having 1 by r partial xi by partial r. Nalaiko. So you are having partial r by partial xi. That's actually xi by r. So this object is actually equal to, this is equal to r by xi. So r and r will cancel out, so I will put that very term here. So it's plus partial f by partial r multiplied by xi by r. Sorry, it will be xi square. So it is r by x, this object, so it will be xi square by r. Okay? So then you are having one more term here, plus partial f by partial r, xi square xi square by r. Is it correct? No, it's not correct. Somewhere there is a mistake. Anybody? So 1 will be 1 by r. So it's 1 by r. Oh yes, it's 1 by r. Oh sorry. This is simply okay. Let me write it. Let me write this in term. So it is 1 by r. Then you are having this as r by xi multiplied by xi by r. Okay. So this is simply 1 by r. Okay. So this is simply 1 by r. Clear? Now is it okay? So this is simply 1 by r term. Okay, now look here. So when I sum over I, so this will be r square. So let me write. So it's r square by r square minus partial f by partial r. So xi square will be simply r square divided by r cube plus. So now there is no sum over x. There is no xi, is it? So how many terms you are summing over I? So these will be m terms, is it? So it will be simply. Oh, okay. So it is simply sum over I goes from 1 to m acting on 1, is it? So it is m, simply. So it will be simply m by r partial f by partial r. Okay, so r square and square will go, it will be 1 by r here. So this will go, it is simply partial to f by partial r2 plus m minus 1 divided by r. Okay, you take m minus 1 divided by r partial f by partial r, simply. Okay? Clear? So this I can put it in this way, 1 divided by r raised power m minus 1, like this thing, partial by partial r raised power m minus 1, partial f by partial r. So if you are having, okay, so this is actually the Laplacian spherical polar coordinates, okay, when you are having the symmetry in this problem. When the function is spherically symmetric, okay, so that means you can put, so this is the Laplacian. So this is the Laplacian, you are having only the radial coordinate dependence, is it? So because f does not have any what dependence, theta and phi, okay? Clear? So samajh aa? So this is, okay, if you are having spherically symmetric problem, you simply write only the radial equation for that problem. Clear? So samajh aa? So now I can write, since you started with the g, okay? So you are having this nebula square g of x, so that's equal to delta of r divided by r raised for m minus 1 omega m. So this is a spherically symmetric object, is it? So it depends only on r. We have argued for that. Okay, so I can write this thing. So this nebula square g I can simply write 1 divided by r raised for m minus 1 partial by partial r. Okay, r raised for m minus 1 partial g by partial r, that's equal to delta of r is m minus 1. Okay? Samajh aa? Clear? Everybody got it? Huh? Okay. So this cancels with this thing. Okay? So now you can integrate over r. Over r, first integration, so it will be, so you put an integration, so it will be simply, okay, let me write d by dr, r is, so it will be, partials will be simply total derivatives, because there is no other dependence in the, in this g. Okay, r, so that's simply equal to delta of r dr. So this is equal to 1, so 1 by omega. So it will be simply r raised for m minus 1 dg by dr is equal to 1, right? Clear? So now you take r raised on the other side. So which implies now you are having simple differential equation dg by dr. So that's equal to So it is 1 divided by omega m, r raised power m minus 1. What is that? R raised power 1 minus m divided by omega. Okay? समझ आया? Got it? So now you integrate it again. Integrate again over r. So it means simply it is g is equal to 1 by omega m integration r raised power 1 minus m dr. Okay, so what is that equal to? 1 by omega m. What? How much is r raised power 1 minus m? So it's r raised power 2 minus m divided by 2 minus. So that's simply equal to minus, okay, 1 divided by omega m into m minus 2, okay, divided by r raised power m minus 2. Clear? So now if I take m is equal to 2, there is a problem. Huh? So I need to take m equal to 2 separately. So if I put m is equal to 2 here, that means in 2 dimensions, I am having a problem with this Green's function. So let's write in the Green's function. So Green's function in m dimensions. So it's simply equal to 1. What is omega m? So it is that. So it will be simply gamma m by 2 divided by 2 into 2 minus m pi raised power m by 2, okay, 1 divided by r raised power m minus 2. So m is actually greater or equal to here in this case. Now let's take m equal to 1 separately. Sorry, m equal to 2 let's take separately. Why I will take? Because our final difference integration I am doing in this very equation, is it? So let's call this equation to be, let's call this equation 1. Let's take m equal to 2 separately. So we are done almost. So in other words, you are having a point charge, is it? Okay, you are so this is actually the Green's function for a point charge in m dimensions. Clear? So let's take in a moment, if you take m is equal to 3 simply, let's take m is equal to 3. So m you take 3, it will be 1 by r, is it? So we have seen yesterday Green's function for a point charge is what? 1 by r. Yesterday we have calculated it. Is it? What is gamma of m by? So it is 3 by 2. What that will be simply 1 by 2, is it? So then you need to check. Okay. So there should be pi, is it? So pi. So those will actually cancel with these factors. So it is 2 minus 3. That's minus 1 minus 2. So 2 raised power pi by 3 by 2 will be like this thing. Yeah? Okay. So you need to check it. Okay. So now let's take m is equal to 2 separately. So from equation 1, so I will write dg by d omega, that's equal to 1 divided by omega 2. Now m is equal to 2, is it? So solid angle in 2 dimensions. So it is r raised power 1. 2, and that may write 2 minus 1. So that's simply 1 by r. It's a logarithmic singular here. Okay. So which implies that g is equal to 1 by omega 2 integral of dr by r. What is that equal to? 1 by omega 2. So that's rest of order. Clear? समझ आया? So in other words, in 2 for m is equal to 2 in 2 dimensions. 2 dimensions. Your Green's function is simply equal to what is omega 2? That's actually 1 by 2 pi should. It should be 1 by 2 pi something. Yes, it should be gamma of 1 by 2 is 1, is it? What is gamma of 1 by 2? What is gamma of 1 by 2? Pi, is it? So just check it, omega. So it is simply equal to natural log of r. Just check it. So it's 1 by 2 pi natural log of r. Okay. Clear? So it's like this. So whether you will be getting here 1 by 4 pi, so it doesn't matter. A constant factor you will get. Because we have not defined differential equation. Delta function we have not taken multiplied by some factor, is it? If you remember defining the Green's function, we are not, in the previous problem yesterday, we have multiplied delta function by 4 pi, is it? That's why we got Green's function to be equal to 1 by r. If I don't multiply it by the, this factor, so what I will get? I'll get simply 1 divided by 4 pi r, is it? So much sure? That simply those factors doesn't matter here. Eh? So this is your Green's function. What it means? So in 2 dimensions, it's a very special thing. What it means? So try to think over it. Why there is a natural log in the Green's function? Eh? So what it gives me? What kind of log is not a good function? Eh? Okay, it's not. I mean, it's not a. It's not that good. That's not. I mean. So how? What is the range of natural log function? Let's say log of x. How far? What? How it looks? What is the graph looking like? Huh? Try to draw the graph of log. Is it? So and see. It starts and it decays. It's a very short range function. Okay. So that means in 2 dimensions your. I mean, interaction is screened. So this is a very important point. Think over it. Okay. So this finishes our discussion, formal discussion on the Green's functions. Okay.